In this video, we are going to introduce some of the important concepts related to performance and parallel computer architectures. We will start the discussion by introducing some important terminology. For instance, we'll talk about response time, throughput, we'll talk about bottlenecks in performance. We'll also talk about some physical and theoretical limitations that dictate these performance bottlenecks. We will then talk about Amdahls law, which is one of the most important and foundational laws that is employed in evaluating performance of parallel computer architectures. And finally, we'll talk about the overall system, computer system performance in light of all of these above discussion. Towards the end of this video, we will introduce parallel computer architectures. We will essentially talk about several types of parallelisms. We'll then look at a popular classification of various parallel computer architectures, and finally we'll go through the spectrum of various different types of parallelisms that are present in modern computer systems. So let's get started with some basic terminology over here. A task is defined as any business oriented unit of work. So for instance, serving a web page or any piece of requested web content could be a task for a web server. Response time is defined as the total time that elapses from the beginning to the end of a task. So essentially, the execution duration of a task is the response time. Latency is also defined similarly. Throughput is defined as the total number of tasks that are completed within a specific time interval. So for instance, if a web server is able to service 1 million web pages every second, its throughput would be 1 million per second. So essentially, the throughput is number of tasks completed per unit time. There is an interesting relationship between throughput and response time. So throughput is essentially inverse of the response time. So for instance, let's assume a website can serve one web page in 1 millisecond, and 1 millisecond is essentially 10 to the power minus 3 seconds. So if the website can serve one web page in 10 to the power minus 3 seconds, this implies it can serve in 1 second, it can serve 1 over 10 to the power minus 3, that is 1000 web pages or 1000 requests. So the throughput of this website would be 1000 requests per second. However, this relationship between throughput and the response time would break down if there is any kind of parallelism or concurrency present in your system. So let's extend this example over here. Now let's assume instead of employing one web server, the website employs two web servers, and each server can serve 1000 requests per second. So this means the overall throughput of the website will be twice as much. So the overall throughput will now go up to 2000 requests per second, which is clearly much greater than what was implied by this relationship over here. Let's think a little bit about the source of this execution time or response time of our programs. The source of this response time really depends on the kind of program that we are executing. Broadly speaking, our computer programs can be divided into two: batch programs and interactive programs. Batch programs are also known as CPU bound programs, and interactive programs are also known as IO bound programs. If you look at the execution lifetime of a batch program, it would look something like this. Let's say the execution starts here, continues for a while, and let's say it ends over here. This is the start, this is the end. So during this period, you'll find that the batch program executes on the CPU for a while, then for some time it does some a little bit of IO, and then it again executes on the CPU for a while, then maybe it again does a little bit of IO, and then let's say it again executes on the CPU for a while and then ends. So essentially, if you look at this lifetime, let's say the time is increasing towards the right, you'll find that vast majority of its time the batch program spends executing on the CPU, and that is why these programs are also known as the CPU bound programs. As opposed to this, if you look at the lifespan of an interactive program, it would look something like this. So let's say this is the lifespan. The program starts over here, and let's say it ends over here. you'll find that the program starts and let's say it executes on the CPU for a little bit, and then it does IO for a while, and then let's say it again executes on the CPU for a little bit, and then it does IO again for a while, and then at the end executes on the CPU and finishes. So here notice that most of its execution or most of its lifetime, the interactive program is spending doing input output, and that is the reason these programs are also known as IO bound programs. You can think of the batch program as let's say a scientific simulation. Once you have set it up, it's most of the time it is spending doing computations on the CPU. It spends a very little amount of time reading the data from the file somewhere in between. As opposed to this, the interactive task, most of the time it is waiting for user input. Irrespective of the kind of task or program you're executing, in general, the response time of a program would depend on two factors. So first, how much actual work your program is doing. So for instance, if you have a batch task and it is spending most of its time executing on the CPU, and you want to make this faster, then employing a faster processor would help expedite the execution of this batch program. The second important factor that would determine the response time is the time it takes to get access to the CPU or other IO devices. So let's say there is only one CPU in your system, and there are 10 different processes that are competing for CPU time. Now in this case, since there is only one CPU, the programs or processes might spend a lot of time in the queue waiting for their turn to execute on the CPU. So in this case, if you employ a faster processor, it will certainly help clear out the queue faster. However, a more effective way of reducing the response time in this case would be to employ more processors, right? So instead of one CPU, you employ 2 or 4 or 8 processors, so that multiple processes can execute in parallel and there will be shorter queues. So having talked about response time, let's now the next time that we want to talk about is bottlenecks. So what is a bottleneck? So given any task, it can be divided into several subtasks. Now the performance of a task is often dictated by a subtask that takes significantly longer than all other subtasks. This subtask is known as the bottleneck subtask or the bottleneck in performance. So let's take a very simple example. Let's assume that we have a task that wants to read a bunch of numbers from the hard disk, sort these numbers, and then print the sorted numbers on a printer. So there are three things we are doing. So we want to read the numbers from the hard disk, then we want to sort these numbers, which will happen in the CPU, and finally we would want to print these sorted numbers using a printer. So let's think about how much time each of these tasks might take, right? So if you're reading the bunch of numbers from the hard disk, this may take let's say a few milliseconds, or let's assume it takes 1 millisecond. Assuming that we have a very efficient sorting algorithm and we don't have too many numbers, sorting in the CPU may take, let's say, 1 microsecond. Now it doesn't matter how fast your printer is, printing this bunch of numbers can easily take a few seconds, right? Let's say it takes 1 second. So in this example, you can clearly see that this third subtask over here, right, this printing task, it takes several order magnitude more time as compared to the other subtasks over here, right? So this printing is the bottleneck subtask in our task. There are many sources of bottlenecks in our computers and in our programs. So for instance, there could be physical and theoretical limitations. So in this printer example over here, right, so this printer, it's a mechanical device. It has physical moving parts, right? So each part can only move so fast. The theoretical limit on the speed of any moving part is the speed of light, right? So that's those moving parts, they pose a bottleneck over here in this printing task. Similarly, when you're trying to access some data over a piece of wire, right? So the electrical signals can only travel so fast. They cannot go any faster than the speed of light. So that's an example of a theoretical limitation that is that may also sometimes lead to bottlenecks. Now, the bottlenecks don't always come from such theoretical and physical limitations. Sometimes it's also programmer fault. So for instance, in this example over here, if a lousy programmer were to implement this sorting task, he or she may come up with let's say O of n cube or O of n to the power of 4 implementation for sorting, right? So in that case, this inefficient implementation can itself lead to bottlenecks. So that's another source of bottlenecks. And finally, there could also be sharing of resources going on in the system, which leads to bottlenecks. So for instance, on the previous slide, we saw an example where there was only one CPU in the system that was shared between, let's say, 10 or 20 different processes, right? So in this case, uh, if your CPU is a unicore uniprocessor machine, at any point in time it can only execute one process, and all other 19 processes would need to wait for their turn to execute on the CPU. So this kind of sharing of resources can also lead to bottlenecks in the system. In general, the key to improving a computer's performance is to either avoid, somehow eliminate, or hide the performance bottlenecks, right? So for instance, if it's a problem of inefficient implementation, make it efficient, right? So that will eliminate the bottleneck. Similarly, if a task can be done in better ways, maybe by employing parallelism in the system or other ways that we'll talk about later in this unit, use those to avoid the bottlenecks. However, sometimes it is not possible to avoid or eliminate the bottlenecks. So for instance, this printing task over here, right? So it doesn't matter how fast the printer is. Even if you employ the fastest printer, it can easily take a few seconds to print the sorted numbers, right? So in this case, if you cannot eliminate the bottleneck, try to hide this kind of bottleneck. And as we will see later on in this unit, one of the important techniques that is employed for hiding the performance bottlenecks is parallelism. So essentially, instead of waiting for the first task to finish, for example, instead of waiting a task to print all the numbers and get done with it, while the previous task is printing on the printer, we can start the next task, and this next task can start reading the numbers from the hard disk and start sorting and so forth. So we'll talk more about this later on in this unit. So let's think a little bit more about the physical and theoretical limitations that appear in our computer systems. So we already talked about the moving and mechanical parts in our devices. Another example of this kind of bottleneck would be if you have, let's say, a spinning or rotating magnetic disk. And let's say the magnetic disk spins at a speed of, let's say, 7,200 rounds per minute. So this is the maximum speed at which your hard disk can spin or rotate. So it doesn't matter how fast your computer algorithm is, the speed at which your hard disk can seek and find data stored in it is limited by this maximum speed. So this may actually cause bottlenecks in your program or in your computer system. Another example of theoretical limits in that dictate bottlenecks is the speed of light in wire delays. There are actually many places where speed of light shows up as a bottleneck in our computer systems, but a very interesting example for us would be that of a speed of a cache. Let's assume we have a cache. So this is our cache, and let's say this is the cache controller. So whatever data you want to send and receive, let's say it has to go through this cache. Now the fastest this cache can serve data would be determined by what is the wire delay between this cache controller and the piece of data that is located farthest from this cache controller. Even if everything else takes zero time, the wire delay, the time it takes for the signal to go to traverse this wire, is dictated by the speed of light. So essentially, as you could imagine from here, the size of your cache in some sense determines the speed with which you can access data stored in the cache. So this is an example of how speed of light and wire delays affect or become a bottleneck in our computer systems. Another source of theoretical limitation is basically complexity of algorithms. So for instance, uh, the fastest you can sort a general piece of data is order of n log n. So if you have n numbers and you want to sort them, you cannot do this any faster than order of n log n. So this is an example of algorithmic limitation. In fact, there are many other algorithms for which no efficient way of solving the problem is known. So those problems actually take much greater than this of n log n time. And finally, there are also thermal limitations that dictate the speed of computations on chips. So for instance, for simplicity, let's assume that in every clock cycle we can finish one instruction. Okay, so let's say this is the clock frequency and this is the cycle time. Okay, so if our frequency is 1 gigahertz, the cycle time would be 1 nanosecond. So which means every nanosecond we can finish one instruction. If we increase the frequency to, let's say, 2 gigahertz, we can finish an instruction every 0.5 nanosecond, and so on, right? So with this logic, if there are, let's say, no dependencies and no other problems, if we go on cranking up the clock speed, the clock frequencies, then we should be able to finish the instructions in our programs faster. But actually there is a problem to increasing the frequency beyond a certain point. And the problem is, as we increase the clock frequency, the power consumption of our chips also increases. And as the power consumption of the chip increases, the heat that is generated during execution of our programs, it also goes up. Now our CPU chips, these are air cooled systems, so there is a limit to how much heat can be safely dissipated using just a simple fan before the chip starts getting too hot and the circuits on chip begin to break down due to heat. In fact, modern processors, they are already consuming 100 to 150 watts of power, which is kind of at the boundary of thermal limits of what can be safely cooled at room temperatures. So essentially, these thermal limits also dictate how fast the computations can be done on our processors and computers. So next, we are going to talk about the Amdahl's law. This is one of the most fundamental results used for evaluating computer system performance. So let's try to derive this law from scratch. So let's assume that we are given a process. The process starts over here and ends over here. And let's say the total time from beginning to the end that it takes for execution is T original. We are also going to abbreviate this time as simply TO. So let's say that this original time it was taking was too long, and so computer engineers and scientists worked hard at this task, and they came up with an optimization that could boost the performance of some fraction of this task. Okay, so let's say we divide the task over here, right? So let's say this is your fraction p, and let's say this is the remaining fraction of your program 1 minus p. So the engineers were able to speed up the execution of this fraction p over here, right? So they were able to, let's say, speed up the execution of this portion by a factor of s. So this portion p now executes s times faster than it was in the original program. And this portion 1 minus p, it still executes with the original speed. There is no optimization in that part of the program. So after this optimization, let's think about what would be the new execution time, right? So let's say t new. So note that this portion 1 minus p, right? This portion, there is no optimization here. So this will still execute with the same original speed. Okay. So if the total execution time of the original program was TO, this portion 1 minus p in the original program would have taken 1 minus p times t original time. Okay, and in the original program, this remaining portion p, this would have taken time p times t original. Okay, however, in the new system we have boosted the performance of this portion p, and it is now executing s times faster. Okay, so what that means is this portion p of the program will now take time p times to divided by s. So this is our new execution time for the program. Now the question is, what is the speed up that we have achieved in this new system or in this new program as compared to the original program? So always remember, speed up is basically defined as the ratio of the original execution time and the new execution time, right? So so this is a fundamental result that can be used for deriving the speed up of any system. So speed up is basically the original execution time divided by the new execution time. So in this system, the original execution time was this TO over here, and here we have the new execution time. So let's compute the ratio to figure out the overall speed up, right? So the speed up would be given by the original execution time, which was basically TO, divided by the new execution time, which is given over here. So that's basically 1 minus P multiplied by TO plus P times TO divided by S. So if you do the math, basically this will if you simplify this, you will find that this reduces to S divided by P plus S into 1 minus P. So this expression over here, this is essentially the famed Amdahls law. So what this is saying is, if you have a program or a system and you were able to speed up a portion P of this program by a factor of S, the overall speed up that is achieved in the entire program is given by this expression. So the same result is also summarized over here. Let's now look at an example to understand the applications of Amdahl's law better. So let's assume that we have a computer system and we want to improve its performance. To do that, we have two options. We can either improve the performance of the adder in the computer, or we can somehow boost the execution time for the divider in the computer. If we choose to go with the adder, then we have an optimization A that can double the speed of addition or the adder in our system. And we know that the additions or this adder is used on an average 50% of the time in our computer. So essentially half the operations that are done in our computer, they are using this adder. As opposed to this, if we choose to go with the divider, let's say we want to improve the divider, then we can do this optimization B in the divider, and this optimization can increase the speed of division by a factor of 10 in the system. However, the divider is only used by 1% of the operations that are done in our computer system. Now, an interesting constraint that we have in front of us is that due to time pressures, we can only implement one of these two optimizations, right? Obviously, the best thing would be to implement both the optimizations, and that way we can make best improvements to our overall system performance. But due to time pressures, we can only do one of these two, either optimization A or B, and the question is, which of these two should we choose? So this is a typical question which can be solved using Amdahl's law. Essentially, we can use the Amdahl's law to figure out what is the overall speed up that is achieved in the system. Let's say if we went with optimization A, and then what is the overall speed up if we just went with this optimization B, and then whichever of these two results in the greater overall speed up, that is the one that we should pick. So recall, the overall speed up achieved in a system from Amdahl's law is given by S divided by P plus S into 1 minus P. Okay, so for the two optimizations, we need to figure out the values of S and P and plug them into this Amdahl's law. So we have the adder and the divider. Let's figure out the values of S and P for both of them, right? So the question says the adder is used 50% of the time. So what that means is the value of P for this adder, the portion or the fraction of time that adder is used is 50%, which is 0.5. The question further says that optimization A can double the speed of an adder. So the speed up S that can be achieved for adder is basically 2. Let's now think about the divider, right? So we know that this optimization B, it can increase the speed of the divider by a factor of 10. Okay, so basically the value of S for divider is 10, and we also know that this divider is used on an average only 1% of the time in our system, right? So this value of the value of P, right, this for the divider would be simply 0.01. This is 1%. Now, having done this, from here onwards the problem is really straightforward. We just need to plug in these values of P and S for the adder and the divider into this expression for Amdahl's law and do the math. So plugging in the values of P and S for the adder gives us speed up equal to 2 divided by the value of P is 0.5, so this is going to be 0.5 plus again the value of S is 2, so 2 multiplied by 1 minus P, so P is again 0.5. So if you do the math, if you simplify this will basically reduce to 2 divided by 1.5, which is essentially equivalent to 1.34. So in other words, this is a speed up of by 34%. So speed up of 34%. Let's do the same for our divider, right? So the speed up that can be achieved by the divider is S upon, so S is 10, so this will be 10 divided by P plus S into 1 minus P, so P is 0.01, so we'll say 0.01 plus 10 multiplied by 1 minus P, which is 1 minus 0.01. So again, if you do the math, if you simplify this expression, this basically comes to 10 divided by the denominator reduces to 9.91. So this is actually equivalent to 1.01. So in other words, this is a speed up of around 1% overall speed up. So which of these should we pick? So clearly the adder is providing us a greater speed up, right? A speed up of 34% as opposed to just 1%, right? So we should pick the adder. We should do optimization A in this case. So the question and the solution is also summarized over here. Alright, so in general, computer systems and applications, they can either be CPU bound, memory bound, or IO bound. So CPU bound basically means an application during its execution lifetime spends most of the time executing on the CPU. So for instance, if you have a scientific simulation that does a lot of floating point computations and maybe other mathematical operations, so that could be an example of a CPU bound process. As opposed to this, if the program spends most of its time during execution accessing the values in the memory, then it is known as a memory bound process or application. And finally, if the application is spending most of its time accessing input output devices, so for example loading data from the hard disk or printing values on the printer and so forth, right? So such application will be known as IO bound application. So typically interactive processes or programs that most of the time are waiting for user input, those are good examples of IO bound applications. So in general, if you're trying to optimize the performance of a application or a system, it makes sense to focus on the largest bottleneck in the system. So for instance, let's say you have a program, let's say this is your process, it starts here and let's say it ends over here, and during its execution lifetime, let's say it spends 60% of the time, let's say 60% of the time on the CPU, and then let's say it spends 30% of the time on accessing the IO subsystem, and then let's say only 10% time it accesses the RAM or the main memory. So if you want to improve the performance of the system, it makes sense to focus on the CPU performance, because that is where most of the time is spent. An interesting thing to notice here is, let's say you do some optimization and get rid of a bottleneck, right? So for example here, let's say originally there was only one CPU, right? So there was only one CPU, you upgraded this and system, and now you have a quad core system or 4 CPUs in your system. So the CPU is no longer a bottleneck. So once you get rid of a bottleneck, it is possible that something else in your system can become a bottleneck, right? So it is possible that once you do this upgrade of the CPU, now let's say the processes, the same workload is, let's say, spending only 30% time on the CPU, But now there was only one hard disk, and you did nothing to improve the performance of the hard disk. You did not add more hard disk, you did not make it faster or anything. So it is possible that now your processes in the system, they are, let's say, spending 50% of the time waiting to access the hard disk, and then maybe they're spending 20% of the time on the RAM, right? So you see, now you have a new bottleneck. This hard disk or this IO subsystem has become a bottleneck. Keep in mind that a good system design is balanced. What that means is the performance of all of these three components, the CPU, the IO subsystem, and the memory subsystem, this is balanced, or this is matched, such that none of these three is a significant bottleneck over the others. So next we are going to get started with an introduction to parallel computer architectures. Here we are going to talk about different types of parallelism that are available in our computer systems. Then we'll talk about a popular classification of various parallel computer architectures, and finally we'll conclude this video with a discussion of different types of parallel computer architectures that are prevalent today. So this slide over here summarizes various types of parallelisms present in our computers. So the first we have is instruction level parallelism. Instruction level parallelism implies executing multiple instructions from the same program simultaneously. A classic example of instruction level parallelism is pipelining. Recall, in our 5-stage ANA pipeline, up to 5 different instructions could be executing simultaneously in 5 different stages of the pipeline. So this is instruction level parallelism. Next we have task level parallelism. So executing multiple tasks or multiple sequence of instructions from the same program concurrently, this is known as task level parallelism. This is similar to the thread level parallelism or multi-threaded implementation or execution. So if a process is implemented as a multi-threaded application, right? So let's say this is your process, and there are several threads inside the process. Let's say T1, T2, and T3, right? So these multiple threads, they could simultaneously be executing on different cores of your processor. If you have a multi-core architecture, let's say, right? So T1 is executing on core 1, T2 is executing on core 2, and so forth, right? So these threads, they could execute in parallel concurrently on different cores or different processors of the system. This is task level parallelism or multi-threaded parallelism. After this we have data level parallelism. So this basically implies that let's say you execute one instruction, but that one instruction operates concurrently on multiple several data items, right? So for example, let's say you issued add 10. Now this is one instruction, but as a result of this one instruction, let's say the computer or the CPU performs R1 plus 10, R2 plus 10, and let's say R3 plus 10, right? So this 10 was added to 3 different data items in parallel concurrently as a result of just one instruction execution. This is data level parallelism. We'll talk more about this when we talk about vector operations later on. And finally, this request level parallelism, this is basically concurrent processing of multiple requests in a system. So essentially it's a measure of how many different requests a system can serve simultaneously. So for instance, if you have a web server, and let's say the web server receives millions of requests per unit time, right? So and let's say out of these millions of requests, your web server is able to process, let's say, 1,000 requests in parallel concurrently simultaneously, right? So this is the request level parallelism in your server. So having talked about several different types of parallelisms that exist in our computers, let's now talk about a way of classifying several different parallel computer architectures that are out there. So Flynns taxonomy is popularly employed for this classification, and this taxonomy is actually based on two concepts: instruction stream and data stream, right? So what is an instruction stream? So essentially an instruction stream corresponds to a program counter, right? So how many program counters are there in your computer system? So let's say you have a quad core processor. So a quad core processor has 4 cores on a single chip. Every core has its own program counter, right? So in this case there are 4 instruction streams. Now a data stream basically corresponds to a set of operands. So for instance, if you have deployed a weather monitoring system on a property. So for this task, you would deploy several temperature sensors and let's say humidity sensors across the property. So every sensor is collecting data periodically, let's say every second. So every sensor is actually a source of data, a set of operands, right? So every sensor could be a data stream. So the instruction stream and data stream, they are independent of each other to some extent, and therefore there are four different combinations of instruction stream and data stream. The Flynns taxonomy uses these four different combinations to come up with four different classes of parallel computer architectures. So the first class of parallel computers is if you have a single instruction stream and a single data stream, right? Exactly one program counter and there is only one source of data operands. So this basically refers to our classic uni-core uniprocessor machine that can only do one thing at a time. So that is single instruction, single data kind of machine or computer architecture. So this kind of computer can execute one single process at a time. There is only one program counter in the processor and the data or the operands are also coming from the executing program. Next, we may have a single instruction stream but multiple data streams. So that basically refers to SIMD processors. So this SIMD machine basically refers to a machine computer architecture where you have a single control unit that issues at a time. It will issue only one instruction. Let's say it issues an instruction at 10, but then there are multiple ALUs. There are several ALUs in your system that will carry out this single instruction on multiple data items simultaneously in parallel, right? So let's say this is your ALU 1 2 3, right? And let's say this when this instruction goes into ALU1, it performs, let's say, R1 plus 10, right? Let's say ALU2 performs R2 plus 10, this performs R3 plus 10, and so forth, right? So this is an example of single instruction multiple data architecture, SIMD architecture. Our modern processors, they typically do this kind of SIMD execution for processing graphic material. The next combination we have is multiple instruction streams and single data stream, right? So this is MISD architecture. Now this is actually kind of a weird category where multiple instructions operate upon a single piece of data. Now the problem is it is unclear whether any such machines exist that can do this. So we are not going to talk much about this class. And finally, we have this multiple instructions stream and multiple data streams, MIMD processors. So this would typically refer to any computer system where we have multiple independent CPUs operating in parallel. So for example, our multi-core architecture, let's say we have a quad core or an oct core processor. So what that means is up to 4 different processes or 8 different processes could be executing in parallel simultaneously on these several different cores. Every core has its own program counter, so that's an independent instruction stream, and then every program that is executing it could have its own independent data stream as well, right? So there are multiple instruction streams and multiple data streams that are being processed inside this multi-core architecture simultaneously. Any other multiprocessor architecture or even the multi-computer architectures that we will talk about later on in this unit, they will also fall under MIMD class of parallel computers. And finally, this slide over here shows the entire spectrum of various types of parallelisms that can be introduced in our modern computer systems, starting all the way from on-chip parallelism and going up to internet scale grid computing. So let's start here with the on-chip parallelism. So at the finest level, parallelism can be added on inside a single CPU chip. So recall, we initially started with a single cycle data path of the N architecture, and later on we converted this single cycle data path into a pipelined implementation. This pipeline implementation is actually a form of parallelism that exists on chip. So if we have a 5-stage pipeline, it can be executing 5 different instructions simultaneously in parallel, right? Now, although in our course we only talked about a single pipeline inside a processor, in modern computers inside a given single processor there could be several pipelines working in parallel. So a single processor can have 2 or 4 or 8 pipelines working in parallel. So such a processor would be able to fetch up to, let's say, 8 different instructions in parallel in a single cycle, and such architectures are actually known as superscalar architectures. So this is another kind of parallelism that is available on chip. uh, Additionally, we can include hardware support inside a given processor so that it can execute multiple threads simultaneously. This is known as multi-threading. So this is the third kind of on-chip parallelism. And finally, on a single chip, we now have enough space that we can have actually multiple CPUs or multiple cores, right? So if you have a quad core processor, it has 8 cores on a single chip. So this is multi-core architecture, which is another kind of on-chip parallelism. So all of these features together can provide us a speed of up to a factor of 10 as compared to a purely sequential design for on-chip parallelism. Now, if we want to go further, we want more performance, then we have to actually start adding more CPU boards with additional processing capacity to the system. So such as shown over here. Now these extra CPU boards that are typically added to the system, they have specialized functions. They are optimized to do some specific kind of tasks. So for example, network packet processing or multimedia processing or cryptography. So these specialized processors are known as coprocessors. So for instance, if you have, let's say, a cryptography coprocessor, it would be highly optimized for doing cryptography kind of mathematics or tasks. So the way this works is, whenever the main CPU receives a operation that is related to cryptography, the CPU will simply offload it to the cryptography coprocessor, and the main CPU can do something else in the meantime in parallel. So these coprocessors, for specialized applications, they can give us an additional performance improvement by by a factor of 5 to 10. However, if we want performance improvement by a factor of hundreds, then it is necessary to replicate entire CPUs and make them all work together efficiently. And this is where we enter the domain of multiprocessors. There are two types of multiprocessors that we will talk about: shared memory multiprocessors and distributed or private memory multiprocessors, as indicated over here. As you will see later in the class, that these distributed memory multiprocessors, they are more scalable, as compared to the shared memory multiprocessors. So if we employ this kind of multiprocessing, where there are hundreds of CPUs, where each CPU has its own private slice of memory, and these CPUs are coordinating with each other over a network, an interconnection network. So using this kind of architecture, we can get an additional speed up by a factor of, let's say, 200 to 300. But if we are interested in performance improvements by factors of hundreds of thousands or millions, then we need to enter the domain of multi-computer systems. So it is now possible to lash together entire organizations over the internet to form a loosely coupled computation grid, and these computation grids, like I said, they can provide us a speed up of a factor of millions. We'll talk more about this later on in this course. Uh, so I just now mentioned loosely coupled computation grid, right? So what does this mean? What is this loose coupling versus tight coupling? When two CPUs or two processing elements, they are close together such that they have a high bandwidth and low delay path between them, they are said to be tightly coupled. As opposed to this, if two CPUs or two computation elements, they are far away from each other such that they have a low bandwidth and high delay path between them, they are said to be loosely coupled. Okay, so in this diagram over here, if you move from left to right, these computation elements, these processors, the CPUs, they become more and more loosely coupled. If you were to move right to left, then these processors, they will become more and more tightly coupled. So another way of thinking about this is, if we are on chip, right, on inside a chip, the computation elements, the cores, the functional units within the cores, they are so tightly packed, they are so close together, so there is a low delay or low latency path between the cores, and also the bandwidth of the bus on chip is extremely high, right? So those, the cores that are on the same chip, they're tightly coupled. As opposed to that, if there are two processors that are, let's say, collaborating over the internet, right? So over the internet, there is no guarantee about the bandwidth. The bandwidth is variable. It's not typically not as high as what you get on chip. Plus, there is a long latency, right? One of the computer might be sitting in New York and the other one is probably sitting in London, right? So there probably there's hundreds of thousands of miles, hundreds and thousands of miles distance between these two elements. So this is an example of a loosely coupled computation system. All right, so that brings us to an end of introduction to parallel computer architecture. In class, we'll talk more about each of these remaining listed topics. So we'll talk more, going more details of on-chip parallelism, co-processors, multiprocessors, and multi-computers. We'll also look at some real-world examples of some of these systems. Towards the end, we will talk about some important considerations in programming these multi-processor systems. And finally, we will conclude with a discussion of some popular performance optimizations employed in modern computer systems. Thank you.